ಕರ್ನಾಟಕ ವಿಜ್ಞಾನ ಮತ್ತು ತಂತ್ರಜ್ಞಾನ ಅಕಾಡೆಮಿ ಕಡೆಯಿಂದ ಎಲ್ಲರಿಗೂ ಈ ಸಂದರ್ಭದಲ್ಲಿ ಶುಭಾಶಯಗಳು. ಅಕ್ಟೋಬರ್ ಬಂದ್ರೆ ಇಡೀ ಪ್ರಪಂಚ ನೊಬೆಲ್ ಪ್ರಶಸ್ತಿ ಪ್ರಕಟಣೆಗಾಗಿ ಕಾಯ್ತಾ ಇರುತ್ತೆ. The month of October brings us the news of the Nobel Prize winners. So ಪ್ರತಿ ಬಾರಿ ಹೋದ ವರ್ಷದಿಂದ ನಾವು ಪ್ರಶಸ್ತಿ ವಿಜೇತರ ಬಗ್ಗೆ ಆ ವಿಷಯಗಳ ಬಗ್ಗೆ ಉಪನ್ಯಾಸ ಮಾಲಿಕೆಯನ್ನ ಆರಂಭಿಸಿದ್ದೀವಿ. ಈ ವರ್ಷ 2021 ನಿನ್ನೆಯಿಂದ ಹಿಡಿದು ನಾಳೆವರೆಗೂ 3 ದಿನದ ಉಪನ್ಯಾಸ ಮಾಲಿಕೆಗಳಿರುತ್ತೆ. ನಿನ್ನೆ ಭೌತಶಾಸ್ತ್ರ ಇತ್ತು. ಇವತ್ತು ರಸಾಯನ ಶಾಸ್ತ್ರದಲ್ಲಿ ನೊಬೆಲ್ ಪ್ರಶಸ್ತಿ ಪಡೆದ ವಿಜ್ಞಾನಿಗಳ ಬಗ್ಗೆ ಹಾಗೂ ವಿಷಯಗಳ ಬಗ್ಗೆ ಮಾತನಾಡಲಿಕ್ಕೆ ನಮ್ಮ ಜೊತೆ ಪದ್ಮಶ್ರೀ ಪ್ರೊಫೆಸರ್ ಎಂ.ಆರ್. ಸತ್ಯನಾರಾಯಣ ರಾವ್, ಪೂರ್ವ ಅಧ್ಯಕ್ಷರು, ಜವಾಹರ್ಲಾಲ್ ನೆಹರು ಸಂಶೋಧನಾ ಸಂಸ್ಥೆಯ ಮುಖ್ಯಸ್ಥರಾಗಿದ್ದ ಡಾಕ್ಟರ್ ರಾವ್ ಅವರು ನಮ್ಮ ಜೊತೆ ಇದ್ದಾರೆ. ಅವರಿಗೆ ನಮ್ಮ ಕಡೆಯಿಂದ ಹೃತ್ಪೂರ್ವಕ ಸ್ವಾಗತ ಮತ್ತು ಕೃತಜ್ಞತೆಗಳು. ಹಾಗೇನೆ ನಮ್ಮೊಟ್ಟಿಗೆ ಅಕಾಡೆಮಿಯ ಮಾನ್ಯ ಸದಸ್ಯರಾದ ಪ್ರೊಫೆಸರ್ ಬಿ.ಜಿ. ಮೂಲಿಮನಿ, ಪ್ರೊಫೆಸರ್ ಎಸ್.ಕೆ. ಸೈದಾಪುರ್, ಡಾಕ್ಟರ್ ಎಚ್.ಎಸ್. ಸಾವಿತ್ರಿ ಅಲ್ಲದೆ ಹಾಗೂ ಡಾಕ್ಟರ್ ಪ್ರೊಫೆಸರ್ ಕತ್ತೆ ಶಕುಂತಲಾ ಅವರು ಇದ್ದಾರೆ. ಅದಲ್ಲದೆ ಡಾಕ್ಟರ್ ಕೊಳ್ಳೇಗಾಲ್ ಶರ್ಮಾ, ಪ್ರಸಿದ್ಧ ವೈಜ್ಞಾನಿಕ ಸಂವಹನಕಾರರು ಅವರಿದ್ದಾರೆ. ನಮ್ಮ ಅಕಾಡೆಮಿಯ ಮುಖ್ಯ ಸಿಇಒ ಡಾಕ್ಟರ್ ಎಂ ರಮೇಶ್ ಅವರು, ಸಂಯೋಜಕರು ಶ್ರೀ ಉಮೇಶ್ ಘಟ್ಗೆ, ಇವರೆಲ್ಲರಿಗೂ ಸ್ವಾಗತ. Today, as we just mentioned, the talk is on the Nobel Prize winners for Chemistry 2021, and the speaker is the esteemed biochemist of global standing, Padma Shri Professor M.R. Satyanarayana Rao, former president of the Jawaharlal Nehru Center for Advanced Scientific Research in Bangalore. As we all know him, he's a specialist in chromatin biology and cancer biology with over 6 decades of research and publications, several awards to his credit. And we are grateful to you, sir, that you accepted our request to kindly come on today and give your time to speak on Nobel Prize winners for the year 2021 in the subject of chemistry. These words, I once again thank you and welcome you to this talk series and today's your address on the subject. Over to you, sir. Thank you very much.
Thank you, Professor Ayappa. Can I share the video now with PPT?
Yes, absolutely.
Yes, sir.
So what do I do now? Share?
Share.
Share presentation. Yes, sir. You can open your presentation, sir, now. The full screen is sharing now. Yes, sir.
Yeah, no, it's fine.
Yes, sir. You can make it slideshow, sir.
Okay, is it okay?
Yes, sir. Yes, sir. Perfect, sir. Please go ahead, sir. Thank you, sir.
Thank you, Professor Ayappan, for requesting me to give this overview on the Nobel Prize in Chemistry 2021. As Professor Ayappan mentioned, the month of October is a very exciting and anxious moment for many of the scientists around the world to look for the global contributors in the area of science, in different disciplines of science, or what made an impact and made a change the way we live and then also benefit the humankind. I think this is a very precious moment. I think for many of us to see who will be the prize winners of that year. I think this year Nobel Prize in Chemistry was announced 2 weeks back. I think the 2 awardees which were selected by the Nobel Committee was Professor Benjamin List of the Max Planck Institute in Germany, and then Professor David Macmillan of the Princeton University, USA. For a long time, the chemistry covers physical chemistry, organic chemistry, synthetic chemistry, and then also inorganic chemistry, and also biochemistry. For some time, the prize winners in the area of chemistry were dominated by the biochemists for the last couple of years, because the chemistry has a lot of influence on the biological process. So this was really irking many of the chemists why the biochemists are taking away the Nobel Prize in the area of chemistry. So it's heartening to see that this year's Nobel Prize in chemistry has gone to the hardcore organic chemists, but still it has a lot of implications in the way the biochemistry has developed and the way we understand the biochemistry, then the molecules, the reaction, etc., etc. So I think it's a happy moment for synthetic organic chemists, particularly for recognizing the contributions of Professor Benjamin List and Professor David Macmillan in the area of development of asymmetric organocatalysis. So before I come to their contributions in the area of organocatalysis, I thought that I'll touch upon a few words in the area of catalysis so that we understand the terminology in the area of the catalysis and how the area has developed. Let me define what catalysis is. I think all of us know what catalysis is, just to refresh our memory. The chemistry really flourished in the 19th century. And the chemists were busy in terms of characterizing the chemical molecules and then the reaction, and by putting together what happens. It's a curiosity-driven science in the area in the 19th century. I think there was also a terminology called alchemy, where people try to use mix a lot of things together and see what happens. But slowly, the fundamentals of chemistry started developing, and the basic reactions, what chemists were busy, was if you have two reactions, A plus B, and then when you mix them together, it gives a product C. So also it can give a single chemical molecule like A can also give rise to two molecules B plus C. The other kind of a reaction is A plus B gives rise to C plus D. So chemists were very busy in terms of understanding or discovering new reactions in the laboratory. But during this course of the reaction, several observations are made that if you put into the reaction mix a small amount of the metal, like the example is that if one puts silver into a beaker with hydrogen peroxide, it breaks down into water and oxygen, but nothing happens to silver. So the atom of the silver element stays intact, but the word catalysis catalyzes the breakdown of hydrogen peroxide into oxygen and water. So this was recognized as a concept and the theme. And in 1935, Swedish chemist Berzelius started to use a pattern. You see a pattern in this and wrote in the Swedish Academy of Sciences annual report about a new force that can generate chemical activity. He believed that the substance had a catalytic force and called the phenomenon itself as catalysis. This is how the term catalysis came into being. Let us continue a little bit more of the catalysis. The substance promoting catalysis was termed as catalyst. The catalyst is needed in very minute amounts, not in equivalent amounts into the reactants, and stays intact after the reaction without any transformation. So this is the basic definition of catalyst. A great deal of work has been done since then, since in this area, since Berzelius coined the word catalysis. Now there are now a multitude of catalysts that can break down the molecules or join molecules. So very wide reactions are catalyzed or catalysis used to bring about a reaction in a much faster rate and much more yield more yield of the molecular product can be obtained. Thousands of different substances we use in I think this has great implications in our life. So thousands of different substances we use in our everyday lives, such as pharmaceuticals, plastics, perfumes, food flavorings, are all made using catalysts. And also I should mention here, the entire human life or life in general in all living organisms is again, I'll come to a little later what those catalysts are, is again uses the catalyst or catalysis, which is driven by enzymes. Enzymes are also catalysts. In the human body or the living cell, enzymes function as catalysts driving the reaction. So now it is estimated in the chemical industry that almost 35% of the world's GDP in some ways involved in chemical catalysis. So you can imagine how the catalysis is influencing our life, our physical life, and the environment, and the chemical molecules, what is available for our various daily usage. Continuing, I should also tell about another terminology in catalysis, what is called activation and catalysis. In chemistry and physics, I think it is understood the reactants which are the starting molecules have a certain amount of kind of energy, but they have to be activated to a higher energy to drive the reaction, and this is called activation energy. If you don't have the catalyst, it requires a certain amount of energy to drive the reaction. But in the presence of catalyst, the activation energy needed to drive the reaction is much smaller. And this is the mechanism of how the catalyst drives the reaction. That means catalyst lowers the activation energy to force the chemical reaction to give rise to the products. You can also see in the left-hand side, reactants are have a higher energy, whereas the products which are derived from this reaction have a lower energy. So this can be brought about by heat or any other energy which can be contributing to the chemical reaction. So these are basic terminologies used in the various catalytic catalysis. Also, I want to bring in another terminology which is very relevant for this this year's Nobel Prize, because it's entirely based on the phenomenon what is called stereoisomerism. Yeah, and then this is one of the stereoisomerism is called enantioisomerism. Isomerism are a pair of molecules that exist in two forms which are mirror images of one another, but cannot be superimposed on one another. It's like just like our two hands. Okay, you have left hand and right hand. They are not identical. They are mirror images, but they cannot be superimposed like this, but they can only join as a mirror image. So this is what is called the enantiomerism. Enantiomerism are in every other aspect are chemically identical. But it is distinguished by the direction in which when dissolved in water, they rotate polarized light either dextro to the right or levo to the left. And this is called dextro-rotatory or levo-rotatory. Hence the term coined was optical isomers. When two enantiomers are present in equal proportions, they are collectively referred to as a racemic mixture, a mixture that does not rotate polarized because the optical activity of each enantiomer is cancelled by each other. This is very important. In the early days, when many of the organic reactions were done, particularly the complex organic reactions, there was always a possibility that you get a racemic mixture. That means you can get come a little bit in the next slide. Using giving example, there will be two dextro and levo molecules are generated, which is in equal amount, and because it's a racemic mixture, for using for further utility of this product, you have to purify each one of them. Otherwise, the other optical isomer is very dangerous, particularly in the biological systems. So if you give a pictorially what is dextro and levo, in the left-hand side, I've given two examples, particularly the biochemical glyceraldehyde, the levo L-glyceraldehyde, D-glyceraldehyde. You have the CHO, COH, HCH1, CH2OH. You can see that hydroxyl group and hydrogen are on the two sides here, whereas the D-glyceraldehyde, they are on the opposite side. If the hydroxyl is just a hydrogen, it becomes identical. That means they are superimposable. But if instead of one hydrogen, there's another hydroxyl group, then it is not superimposable. They become optical isomers. The same thing happens in the amino acids, L-amino acids and D-amino acids. The optical isomers are very, very important in biology, particularly in the biochemistry and in terms of the biochemical reaction, the macromolecular synthesis, and the biological function of the macromolecules is entirely dependent on this the optical isomerism. On the right-hand side, another organic molecule, I have given an example, like a limonene and which is S-laminin and R-laminin. And in the space filling model are given there. They're not identical, but they are superimposable. If you can see that S-laminin is present in lemon, it has a lemon taste, whereas the L-laminin is present in orange, but is an orange taste. So you can immediately see the taste receptor in our human body recognizes each specifically differently and generate the signal in the nervous system that this is a lemon taste and this is orange taste. So immediately it is apparent this optical isomers are very important in terms of the biological perception, in terms of how the nervous system recognizes these different molecules, etc. So this gives the importance of the optical isomers. Now, this is some of the terminology which are very relevant, which are important into us understanding what these two Nobel laureates contributed in their work. Before that, I will just briefly highlight catalysis is a very fertile field in organic chemistry. I think you can imagine that, you can realize that in this almost 7 Nobel Prizes have been already awarded in the area of catalysis in chemistry. The present one is in the 8th. Maybe the future, many more may come. I'll come in the last slide about it. The first Nobel Prize was given to Oswald in 1909 for catalysis. P. Sabatier in 1912 for hydrogenation using metal catalysis. Ziegler and Natta in 1963 for catalysis for polymer synthesis. Cornforth in 1975 for stereochemistry of enzyme catalyzed reactions. Rouse, Noyori, and Sharpless in 2001 for asymmetric catalysis. It's not asymmetric organic catalysis, just asymmetric catalysis. Grubbs and Schrock in 2005 for olefin metathesis. Heck, Negishi, Suzuki in 2010 for palladium catalyzed cross couplings. These were the earlier Nobel Prizes given in the area of the catalysis. I'll come to the importance of this the optical isomerism, particularly in the biomedical field. You know, in the year 1956, there is a famous thalidomide disaster, which was very dangerous, and then it was very well publicized in the world. Thalidomide was an organic molecule which was synthesized in the laboratory, was introduced in 1956, and was aggressively marketed by the German chemical company Chemie Grunthal under the trade name Contergan, which was used for anxiety, sleeping sickness, tension, and morning sickness. And at that time, many of the pregnant mothers were also given this drug for managing sleeping sickness, anxiety, tension, etc. But after 2 decades, the after effect of consuming this thalidomide became apparent. Approximately around the 1970s, 80s, it became clear that many birth defects were there in the newborn. Approximately now 100,000 birth defects were reported worldwide because of the consumption of the thalidomide by the pregnant woman. Just a minute, I'll have some water. On the left-hand side, the structure of the enantiomers, R enantiomer and S enantiomer is given. So thalidomide, when it was used, it was a mixture of this R and S forms. So it was prescribed, and then they were going to the pregnant mother. And then S isomer, afterwards they came to know that S isomer alone causes birth defect, and the R form is safe. So you can imagine that one of the isomer is very dangerous. Now we know why the birth defects are formed, because during the embryonic development, one of the key important transition factor is affected by the S isomer. So you can see the consequence of the wrong usage of the wrong isomer in the medical field. So this gives a great importance of the purity of the optical isomers, which is used for the biomedical area. Presently, now we know all this background of the isomerism, etc. Now, presently, the S isomer is used for morning sickness. It's no more prescribed for the pregnant woman. It's completely banned. But it's now used for in the adult for morning sickness, and also for multiple myeloma, along with other chemotherapeutic reagents. So as I mentioned earlier, S-isomer affects limb development in the human embryo. So this gives the importance of the optical isomerism. Now, coming back to the types of catalysts, all catalysts discovered before the year 2000 belong to two different groups. They were either metals or enzymes. Metals have ruled this catalytic area, catalysis area for a long time. In biology, we know the enzymes or the catalysis. Well, I'll come to a little bit later on the enzymes. Among the metals are excellent catalysts due to their ability to temporarily accommodate electrons. You know, all the chemical reactions is based on electron removal and adding to the formation of the chemical bond, etc., etc. So temporarily, the metals, they hold these electrons from the whole molecule and give rise to the different molecule, forming the chemical bond. It is a temporary resident. It resides temporarily in the metal, but the metals are very good, efficient reagent for the holding this pair of electrons. So which helps to loosen the bonds between the molecule and also join the molecules. So that bonds are otherwise strong can be broken and new ones can form. So one of the major problems with some catalysts, many of the metal catalysts, is that they are very sensitive to oxygen and water. So for these to work, they need an environment free of oxygen and moisture. This is very difficult. In the laboratory scale, is fine. See, you can demonstrate and then you demonstrate the reaction and get the product, purify and characterize it. But in the industrial scale, this is difficult to achieve in large-scale industries. Furthermore, many metal catalysts are heavy metals, which can be harmful to the environment. So all the metals have been there in the literature and also in the chemical industry. There are a lot of drawbacks and there are a lot of harmful effects in the environment. Coming to the enzyme, the second form of catalysts are proteins. I think all of us know that many of the proteins molecules are also function as enzymes. All living things have thousands of different enzymes that drive the chemical reactions that are vital for life. Many enzymes are specialists in asymmetric catalysis. That means asymmetric catalysis is that during the reaction, only one optical isomer is formed, not both the forms. So it doesn't generate a racemic mixture. So it is a great advantage to drive the reaction to a particular isomer what you want, which is very important for further utility. And principle, it always form one mirror image of the two that are possible. These enzymes also work side by side. You know, all of us have studied biochemical pathways in many of the cellular contexts. You know, biochemical pathways, you know, the first reaction is catalyzed by one enzyme. The product is taken over by another enzyme and generates the second product. That way, the series of biochemical reactions takes place starting from one starting molecule to the final product. That means the enzymes also work side by side. When enzyme finishes its job, another takes over and can build up complicated molecules such as cholesterol, chlorophyll, or even strychnine. I'll come to strychnine. But this is not possible in the metal-derived catalysis because it cannot. It's not like a conveyor belt. We have to purify the product and then go to the second reaction. It cannot go side by side. So, but the enzyme function this cascade reaction very efficiently in the living cell. But one major problem with enzymes is that they are big protein molecules and expensive. See, there are also have been efforts to synthesize many complex organic molecules using the enzymes also. But the problem is that the major problem is that the enzymes are very big, but the metals are very small. So there's a difference between the size of the catalyst between the metals and the enzyme. Each one of them have their own disadvantages. So there are problems in all these areas. So these are all the questions which have been bothering the chemists for a long time. I'll come to the motivation and the idea behind Benjamin List's discovery, which is drove for his the path-breaking contribution, which earned him the Nobel Prize. I told you just now that enzymes are very efficient catalysts, and therefore in 1990s, scientists wanted to develop new enzyme to to drive the chemical reactions. That means you have an enzyme which is known to perform a particular biochemical reaction. Can you engineer this enzyme to perform some other reaction? That means they wanted to drive or derive enzyme variants to drive different chemical reaction. That means they wanted to engineer the enzyme for different purpose. So this was the kind of work which was going on in Scripps Research Institute, which was led by Carlos Barbas, late Carlos Barbas III, around 1990s. The Benjamin List was a postdoctoral fellow in this work, in this group. So while this work was going on in that laboratory as a postdoctoral fellow, he had a brilliant idea that led to the discovery behind this year's Nobel Prize. So he started thinking that while doing the engineering of the enzyme variants to drive chemical reaction, he started working on catalytic antibodies. Antibodies are proteins which are generated in the immune system in the body, which bind to the viruses and then antigen they can be immunological reaction. Normally, the antibodies are also a big molecule, protein molecule, but they don't have the enzyme reaction. They don't catalyze any enzymatic reaction. So Benjamin List started working. Can you engineer the antibodies which don't have any enzymatic reaction to see whether it can catalyze any enzyme reaction? These are called as catalytic antibodies. That means you want to create a catalytic center in the antibodies to drive the chemical reaction. So this group redesigned this antibody to drive the chemical reaction. And enzymes are usually huge molecules that are built from hundreds of amino acids. All of us know about it. So in addition to these amino acids, many enzymes also have metals that have drive chemical reactions. There are two types of enzymes, metal enzymes, and then some enzymes don't have the metals. That means there are also enzymes that don't have metals, which is important to drive the chemical reaction. Here the reactions are driven, although there are hundreds of amino acids, in the catalytic center, the catalysis is driven by only few individual amino acids in the enzyme. That means one or two amino acids. So he started thinking, Benjamin List, do amino acids have to be part of an enzyme in order to catalyze a chemical reaction? Or could a single amino acid, other similar molecules can do the job on its own? You don't need the entire protein molecule. Just the two amino acids is in the catalytic center. Can it drive the chemical reaction? So I'll give the pictorial representation. In the left-hand side is an enzyme molecule, which is built up by the several hundreds of amino acids. Okay, in the midst of all these amino acids, there are two amino acids in the center, which is in the circle here, which is expanded the right side, and which drive the chemical reaction. And most often in this catalytic center, one of the amino acid is proline, L-proline. So one is proline. So the structure of the proline is given on the right-hand corner. So he started thinking whether he can use just a proline, which is in the catalytic center, to drive the chemical reaction. It's not a metal-driven, but it's not a total enzyme molecule. But the chemistry behind it is that the nitrogen atom in this proline can temporarily house electrons. I told you earlier, the basic definition or the property of the reaction catalyst is that it should hold temporarily the pair of electrons, which can house it and also donate it. That property is there in the nitrogen atom of proline. So this is the publication in the year 2000. I think that you see any major discovery, the first paper in that area is the most important thing. If you read the summary of that paper, it explains everything they did. Okay, this is the first paper which got on the Nobel Prize. Which was published in Journal of American Chemical Society in the year 2000. The title of the paper is Proline Catalyzed Direct Asymmetric Aldol Reaction. In organic chemistry, aldol reaction is a ketone and the aldehyde is driven, condensation occurs to drive the aldol condensation. I want to read the entire abstract because it drives the concept of the Nobel Prize, which is highlighted in the yellow in the left-hand side. The most enzymatic transformations have a synthetic counterpart, often though the mechanism by which natural and synthetic catalysis operate differ markedly. The catalytic asymmetric aldol reaction as a fundamental CC bond forming reaction in chemistry and biology is an interesting case in this respect. Chemically, this reaction is dominated by approaches that utilize preformed enolate equivalents in combination with chiral catalyst. Typically, a metal is involved in this reaction mechanism. Most enzymes, however, use a fundamentally different strategy and catalyze the direct aldolization of two unmodified carbonyl compounds. Class 1 aldolases utilize amine-based mechanism, where class 2 aldolases mediate the process by using the zinc factor. The development of aldolase antibodies that use an amine mechanism to accept hydrophobic organic substrates has demonstrated the potential inherent and amine catalyzed asymmetric class 2 aldolase mimics. I think you can see the enormity of this contribution which is given in this paper. On the right-hand side is given the chemical reaction which he demonstrated. So this is the basic contribution concept which Benjamin List contributed to the area of catalysis. I think which is the foundation of the award of the Nobel Prize this year. Let me also go through the professional career of Benjamin List, just to highlight how we grew up professionally. You know, he was born in 11 January 1968, a German chemist. Now he's presently one of the directors of Max Planck Institute for Core Research and also professor of organic chemistry at University of Cologne. I think he has a very interesting intellectual family background. Born to an upper middle class family of scientists and artists, he is a great grandson of the Christian Vallard, second grandson of the chemist Jacob Vallard. His aunt, the sister of his mother, Christian Nusrein Vallard, is a Nobel winner in medicine and physiology. Okay, his mother, Heidi List, was an architect. So you can imagine the very illustrious and intellectual family background. He obtained his MSc degree in chemistry from the Free University of Berlin in 1993, PhD from the University of Frankfurt in 1997. His doctoral dissertation was on synthesis of vitamin B12 and semicolon. I'll come to vitamin B12 a little later. Okay, he did his postdoctoral research at Catalysis Institute, La Jolla, I told you earlier, with Carlos Barbas, and an assistant professor in 1999 to 2003. In 2003, he returned to Germany as a group leader at the Max Planck Institute for Core Research, where he is also director. He is also an honorary professor at the University of Cologne. He has received several awards: 2003 Karl Duisberg Memorial Award of the German Chemical Society, 2004 Liesberg Prize of the University of Heidelberg, 2005 Novartis Young Investigator Award, 2009 Thomson Reuters Citation Award, 2012 Otto Boyer Prize. You see here, 2017, he came to India. He gave the Professor Ghatak Endowment Lecture at IACS Calcutta, Indian Association of Cultivation Science. So he is connected to Indian scientific community. 2018, member of the German National Academy of Sciences. 2021, with Nobel Prize in Chemistry, is also now selected for the 2022 Herbert Brown Award for creative research in synthetic methods. This is about Benjamin List. Now let us move to the second Nobel laureate, motivation behind David Macmillan. This is the motivation behind David Macmillan to do the Nobel work. David Macmillan was at Harvard before moving to the University of California, Berkeley. He worked on improving asymmetric catalysis using metals. He studied, spent a lot of years using metals to use a different condition to drive the asymmetric catalysis. I told you earlier, in the normal condition, it gives a racemic mixture, which is both the Erlang form, but he used to modify the catalytic reaction conditions, the metal complex, etc., to drive the chemical reaction through the asymmetric catalysis. But he realized these catalysts that were developed were rarely used in the industry because the sensitive metals were quite sensitive and to water and oxygen and expensive use. Achieving the oxygen-free and moisture-free condition is very simple in the laboratory. but very complicated in large scale manufacturing in the industry. Now, when he moved to Berkeley, he left behind the metals. When he got fed up with the metals, there is no use in working metals. It's not going to be useful in the chemical industry because of all these complications. So in Berkeley, he started to design organic molecules, which just like metals can temporarily accommodate electrons. And based on his chemistry knowledge, he thought that the molecule should have a minimum of iminium ion. You know, I was telling about the proline in the atom. Similarly, iminium ion in the organic molecule is in the contain nitrogen, which has an inherent affinity for electrons. Some of the organic molecules were also excellent at asymmetric catalysis. Of the two mirror images, one of them comprised more than 94% or 90% of the product. So he was the person who coined the word organocatalysis. And then now we know the combination of organic catalysis and the asymmetry, the area is now called as asymmetric organocatalysis. Now this is his paper. Okay, just like Benjamin's list, the paper of David Macmillan also appeared in the year 2000, Journal of American Chemical Society in 2000. Just like, I don't want to go into the right-hand side chemical reaction. I'll just read just like the highlights of the abstract, just like I read about the Benjamin list. In the abstract is given, over the past 30 years, enantioselective catalysis has become one of the most important frontiers in exploratory organic synthetic research. During this time, remarkable advances have been made in the development of organometallic asymmetric catalysis that in turn have provided a wealth of enantioselective oxidation, reduction, pi bond activation, and Lewis acid catalyzed processes. Surprisingly, however, relatively few asymmetric transformations have been reported which employed organic molecules or reaction catalysis. Despite the widespread availability of organic chemicals in enantiomer pure form and the accordant potential for academic, industrial, and economic benefit. So this also opened up the area to design several new organocatalysts, which are enantioselective, which drive the asymmetric catalysis. If I see the professional career is also very distinguished professional career, he was also born in 1968. It's coincidental, both the Nobel laureates were born in 1968. And also you can see that the Nobel Prize winning work was achieved or conceived at the age of 32. So 2000 was the year when the first paper was published. So the work was conceived and conceived, proven, and demonstrated at a very young age. So this recognition is waiting for a long time for the world to recognize this work. More importantly, I think they did the phenomenal and fantastic work at a very young age. Age is not a criteria when you do the Nobel Prizing work. It can be in the very young age. You may be thinking out of the box and then really create a new area for yourself, or build up a lot of work. Sometimes you do the Nobel Prize work at the age of 50, 60. So there are several examples. The age is not a real criteria when the Nobel Prize work is done. But just to highlight, at the very young age, they really thought out of the box and did really contribute extensively to the area of organic catalysis and asymmetric organocatalysis. He's a Scottish person. He was born in Belshire, Scotland. Received an undergraduate degree in chemistry at the University of Glasgow. In 1990, he left UK to begin his doctoral studies at the University of California, Irvine, under the professor Laurie Orman, focused on the development of new reaction mechanism toward the stereo-controlled formation of bicyclic tetrahydrofurans. It is a postdoctoral research at David Evans at Harvard University. Started his independent career as a member of chemistry faculty at the University of California. He joined the chemistry department at Caltech in June 2000. And then in 2004, he was appointed professor of chemistry at the Princeton University. He has held a very distinguished professorship. In 2000, when this paper was published, along with that, he designed several organic molecules that can provide or accept electrons and therefore efficiently catalyze reactions. They applied these new molecules to synthesize range of complex natural products He's also the founding editor of Journal of Chemical Science, and then he has received Corday Morgan Medal, Royal Society of Chemistry, 2012 elected to the Royal Society, member of the Academy Award of Arts and Science, 2017 Nobel Prize, 2018 member of the National Academy of Science USA, and 2021 the Nobel Prize. Two very distinguished chemists who did the path-breaking discovery at the very young age of 32 have been recognized in this year's Nobel Prize. So on the left-hand side, you are given the chemical molecule, which is the first generation of chiral imidazolidinone catalyst, which is famous in the organic catalysis area. So what is the advantage of all this organocatalysis? I think I'll give one example of, in terms of the advantage of this. Since 2000, after the discovery of organocatalysis, this area is considered like a gold rush in the chemical reaction. I think that both Benjamin List and David Millen are really considered stars in this area, even before the Nobel Prize was given to these two people. Another major advantage of organocatalysis is that they can work as a conveyor belt like enzymes. I told you in the ordinary metal catalyzed reaction, it cannot be done as a conveyor belt. You have to purify each of the product at each step. But in the organocatalysis, it can act as a conveyor belt. Okay, and this is the major advantage. And then also, it was necessary to isolate and purify each intermediate product. Either the volume of the byproducts would be too great. In organocatalysis, several steps in a production process can be performed in an unbroken sequence, which is called as a cascade reaction that reduces wastage in chemical manufacturing. See, I'll give an example. The right-hand chemical formula is strychnine. A classical example of this advantage is the synthesis of strychnine, a naturally occurring molecule. And when strychnine was first synthesized in 1952, it required 29 different chemical reactions, and only 0.0009% of the initial material was strychnine. In 2011, using organocatalysis and cascade reaction, strychnine was synthesized in just 12 steps, and the production process was 7,000 times more efficient. So you can see the contribution of this organocatalysis, not only in terms of efficiency, but also the purity of the product which you can obtain. I'll give another side example here. Most of the organic chemists are very fascinated. Many of the biological systems, particularly in the plant area, phytochemicals. The plant biologists want to discover new phytochemicals for many of the pharmaceutical applications for medical use, etc. So they keep on discovering new complex molecules in terms of these various plants across the world. So whenever I discover a complex molecule, I think like they may be present in very small amount in many of the plant species. Okay, the task for the organic chemist is can you synthesize this complex molecule in the laboratory. One is the intellectual challenge. The other is that can you cut down the cost of this production, because you have to grow a lot of plants to derive a medically important compound from the plants. So there are two challenges here. I'll give one example why the organic chemists are challenged by the organic synthesis. The left-hand side is the structure of vitamin B12. I think all of us know vitamin B12. Vitamin B12 is important for growth and the cellular reproduction, blood formation, and protein synthesis. The absence of vitamin B12 causes anemia, fatigue, and numbing, etc. The crystal structure of vitamin B12 was solved by Dorothy Hodgkin, who developed the external crystallography for macromolecules and then solve the structure of insulin. Now, this is the important biological macromolecule. Now, there was one famous organic chemist at Harvard at that time, around 1960s. He took up a challenge: can I synthesize this vitamin B12 in the laboratory? The total synthesis of vitamin B12 was accomplished in two different approaches by the collaborating groups of Robert Barnes Woodward at Harvard and Albert Kanmoser at ETH, Switzerland, which required 91 postdoctoral researchers and 12 PhD students.
To make this total synthesis, it required so many man hours, 91 postdoctoral researchers and plus students, because it has to be the right bond, right optical isomer. I think you can see the enormity of the challenge. What he could achieve with so much manpower. For this phenomenal achievement, Robert Woodward was awarded the Nobel Prize in Chemistry 1965. So this kind of a intellectual challenge still exists in many of the organic chemists today. Now, so when the challenges are there, and particularly when you want to develop synthesis methodology and reaction procedure, particularly to derive a particularly important optically active molecule, then the contribution of this asymmetric organocatalysis becomes a great contributor, a great benefactor. I think you can see the enormity of the contribution of asymmetric organocatalysis. In asymmetric organic catalysis, you can see the application in pharmaceutical industry. Has a very significant impact in pharmaceutical research. It frequently requires asymmetric catalysis for many of the reaction mechanisms. Until chemists could perform asymmetric catalysis, many of the pharmaceuticals contain both mirror images of a molecule, among which only one was reactive, but the other could be deleterious, a lot of side effects. Just like I told you about the thalidomide story, I was just mentioned about it. So using asymmetric organocatalysis, research can now make large volumes of different asymmetric molecules. They can artificially produce potentially curative substances that can otherwise only be isolated in small amount from rare plants or deep sea microorganisms. This is the future. Now, coming to the summary or summarize everything, simple ideas are often most difficult to imagine. So after listening to all this, it is a very simple idea. Use a problem and do the reaction. But so out of the box thinking, that is the creativity. Nobody has thought about it. You can think about the simple thing, but make a big, the greatest impact of the humankind. Most often our view is obscured by the strong preconception about how the world should go. Okay, we are preconceived. Oh, it should happen like this. It should happen like this. Nobody thinks about, why can't the different way? So that is the kind of out of the box thinking. I think many of the discoveries have come by the simple idea through out of the box. Organocatalysts are now bringing the greatest benefit to mankind thanks to the discovery and contribution of Benjamin List and David Macmillan work. So what is the future of the catalysis? I thought I'll just bring into the attention of the kind of experiment which is going on in the area of catalysis. What holds the future for catalysis? There are two major challenges for humankind. One is the carbon dioxide fixation. The climate change, the culprit is the emission of carbon dioxide, which is present in the atmosphere. The challenge is how to reduce the carbon dioxide. One is to minimize the production of carbon dioxide through not using the fossil fuels. The other thing is, can you decrease the carbon dioxide which is already present in the atmosphere? So can you use the phenomenon of artificial photosynthesis, where you can convert the carbon dioxide to methane and other carbon products. So a lot of work is going on in this artificial photosynthesis. Many of the catalysis have been discovered, but still it is still in the exploratory stage. I think it is possible in the down the line, many of the maybe new catalysts may be discovered where the artificial photosynthesis becomes a norm, but doesn't stay only in the laboratory, but it can be done in the much larger scale. The other is the hydrogen fuel. Again, the fossil fuels are becoming scarce and scarce. I think we need alternative energy. One is the solar energy. The other energy which is being thought is the hydrogen fuel, using the hydrogen gas as the source of energy. I think again, a lot of research is going on. We already have the cars which is run by hydrogen fuel. But again, the generating hydrogen fuel and storage, I think is a very challenging task. I think there is another interesting concept or the area which is developing is called water splitting. Water is very abundant in the earth, Okay, there's so much of water. Can you use this water as a source of hydrogen? Okay, so this is like a water splitting where you can use water using appropriate catalyst. I think even graphene is used in this area to in the graphene in complex with other small molecules to split the water to generate the hydrogen. Again, both these areas in the use of catalysis is still in the infancy state. Many of the chemists believe there will be a great achievement in the near future. I think the catalyst, the Nobel Prize, is not the end of the Nobel Prize for catalysis yet. I think many more Nobel Prize may be awarded to the area of catalysis. I think the organic chemists are really having a lot of challenges in the future. This is the end of my presentation. I thought I would give a glimpse of some principles of catalysis, and then the two types of catalyst, metal catalyst and the enzyme catalyst. The enzyme catalysis, how would give an idea for the organic chemist to derive the organocatalysis and also use stereoisomerism and design the small proline or iminium-based small organic molecule to drive the enantioselective catalysis for many of the organic synthesis of synthesizing many organic molecules, so which are beneficial for the humankind, not only in terms of the material size, material benefit, but also for the human health. Okay, thank you. I'll conclude here. Thanks for KSTA for inviting me to share my views on this Nobel Prize in Chemistry this year. Thank you, Professor Ayappan.
Thank you. Thank you very much, sir. Grateful to you for this a brilliant exposition of the Nobel Prize Chemistry 2021 and also very lucid explanation of the entire background that led to this Nobel Prize in Chemistry. ನಮ್ಮೊಟ್ಟಿಗೆ ಇವಾಗ ಖ್ಯಾತ ವಿಜ್ಞಾನ ಬರಹಗಾರರು ಶ್ರೀ ನಾಗೇಶ್ ಹೆಗಡೆ ಅವರು ಕೂಡ ಇದ್ದಾರೆ. This time, at this time, any comments, suggestions, remarks from our audience, you are welcome. Professor Rao is with us, please. Any comments?
Sir, there is one question from the participants.
Yeah.
What is your opinion on application of organocatalysis in food industry, sir?
Food industry is a very broad-based in terms of the food industry. What we think about is only food processing of in terms of using the natural product to process the appropriately edible product. Okay, so there also many of the enzymes are used. I think there is a possibility of using organocatalysis there, where you can minimize the use of enzymes. Okay, I told you earlier, enzymes, there is a drawback because of if you want to use the enzyme in bulk, even the production of enzymes is also costly. And also in terms of the bulk usage of the enzyme, it becomes economically little costly. So if you can design organocatalyst for the kind of food industry, I think it will be great. I don't know what is going on in that area, but potentially usable.
Thank you very much, sir.
Any other remarks from our colleagues, audience? Yeah. So,
Sir,
Professor Mani,
particularly in the area of this water splitting, are our laboratories engaged in this kind of thing in India? This, with regard to
No, many people are doing this organocatalysis here. I told you after 2000, this area has really opened up. Organocatalysis is almost a regular thing in many of the organic synthesis laboratories, even in the chemical industry.
yes, sir.
because we have a hydrogen mission now recently announced, so this area must be being addressed in the country. Any other remarks, suggestions, opinions? Yeah, so thank you very much. Grateful to you, sir, for this
Thank you, sir.
time and as I said, sharing your perception of the Nobel Prize Chemistry 2021. Grateful to you. Over to Dr. M. Ramesh, CEO of the Academy, for his words.
Good afternoon. We have listened to a very scholarly and distinguished talk by eminent scientist and former president of JNCSR, Padma Shri, Professor MRS Rao sir. Professor gave a glimpse of the research contribution of this year's chemistry Nobel laureates. Professor Benjamin List of Max Planck Institute, Germany, and Professor David Macmillan of Princeton University, USA. Their research on the development of asymmetric organocatalysis were presented by Sir. Sir spoke about the basics of catalysis, activation energy, then enantiomerism with examples and thalidomide disaster, etc. And Sir briefed on the research of both the Nobel laureates with their earlier works also. And also, Sir gave a glimpse of the future of catalysis, especially artificial photosynthesis and hydrogen fuel. Sir, on behalf of KSTA and all the participants, I'm immensely thankful to you for this very scholastic and enlightening talk. Thank you very much, sir.
Thank you.
I'm grateful to our Honorable Chairman, Professor S. Ayappan, sir, for initiating and encouraging us to organize this series of Nobel Lecture Series. I'm also thankful to our esteemed KSTA members, Professor B.G. Murimani, sir, Professor Saidapur, sir, Professor Katre Shakuntala, madam, Professor H.S. Savitri, madam, and Professor Nagesh Agde, sir, for their presence in the webinar. I'm also thankful to Professor H.R. Rangnath, sir, for suggesting us to organize such a series of Nobel Lecture Series last year. Based on that, we are continuing this year as well. I would like to thank senior academicians who are present here, Dr. Prabhudev, Dr. Abhishek, Dr. Mukunda, Dr. Santosh, Dr. Manjana, Dr. Manu Kumar, and all the young students, PG students and PhD scholars who are present here. Tomorrow we will be having a talk on Nobel Prize in Medicine, Physiology by Dr. Bhupesh Mehta, who is the professor of biophysics in NIMHANS. I invite you, all of you to join the talk like today and yesterday and make it a success. Once again, thank you all. Thank you very much, sir.
Thank you, sir. Thank you very much. Grateful to you.
Thank you.
Grateful
Thank
to
you.
Dr. Rao and everybody here. Thank you.
Okay, thank you. Thank you very much. Thank you very much.
Thank you, sir.